Quantifying uncertainty in the heterogeneous ice nucleation rate coefficient, or J-hat. And J-hat is simply a variable that tells you how likely a freezing event is to occur when a water droplet is in contact with some surface. In order to get a measurement of J-hat, we placed water droplets on sheets of mica which were set up on a cooling stage. As we bring the cooling stage to colder temperatures, the water droplets will begin to freeze or undergo a nucleation event. When a nucleation event is observed for a droplet, the temperature of the cooling stage is recorded. The resulting data set that we are left with is simply a list of freezing temperatures, each corresponding to the freezing of one of the droplets. The mica sheets were treated with a chemical solution to replace the naturally occurring potassium surface ions with bivalent and trivalent ions, which are listed on the slide. The goal of this experiment was to see if the nucleation rate coefficient J-hat was affected by the presence of different surface ions. This diagram is a visual interpretation of the data set. Each bar is representative of one droplet from the experiment. The blue portion of the bar indicates that the droplet was liquid, and the red portion signifies the droplet has undergone a freezing event. The numbers at the bottom of the chart represent increasing time bins of arbitrary units. J-hat is calculated by measuring two variables, N-nuc and T-tote, within each bin. N-nuc is simply the number of nucleation events in a given bin. If we consider bin 4 in this chart, N-nuc would equal 3 for the 3 instances where the bar changes from blue to red. T-tote is the sum of the liquid time for the frozen droplets and the liquid time for the unfrozen droplets. So for this graphic, we would be adding up all the blue parts of the bars in bin 4. Note that 2 of the bars are red before the start of bin 4. These droplets are not included in the calculation of T-tote because there is no new information coming from the frozen droplets. When we divide N-nuc by T-tote, you get freezing events per unit time, which is a quantity related to J-hat we will call omega. To obtain the true units of J-hat, we must also account for the surface area of the water droplet. Thus, the final units of J-hat are freezing events per unit time per unit area. This is a plot of the results from the previous experiments done by our collaborators. An increasing J-hat means that a freezing event is more likely to occur. So these results suggest that a freezing event is more likely at warmer temperatures for a water droplet in the presence of trivalent surface ions as opposed to the bivalent ions, which themselves seem more conducive to freezing than the monovalent potassium ions. However, you should note that there are no error bars on this plot. This is because our experimental setup requires more extensive error analysis than a simple mean and standard deviation calculation. Obtaining a better sense of the uncertainty of our measurements was the primary goal of our work this summer. These two equations are from a paper by Coop et al., which are derived via statistical argument connected back to experiments measuring J-hat, much like the one I described before. When you solve these equations for omega low and omega high, you obtain an uncertainty bound for the variable omega, which you may recall is in units of freezing events per unit time. X on the left-hand side is an uncertainty parameter related to the probability that the measured omega is between omega low and omega high. To verify the statistical claims in the Coop formulation and develop another way of obtaining uncertainty bounds, we created a computer simulation that replicates our freezing experiment in a virtual setting. If we assume that the freezing of any one droplet is independent of another freezing event, then the freezing times of a set of water droplets should be exponentially distributed. The shape of this distribution is determined by a parameter mu, which is representative of the cooling rate from the real experiment. Thus, if we draw freezing times from this distribution for a given number of droplets, big N, we have essentially created a virtual isothermal version of the real experiment where we can calculate T-tote, N-nuc, and omega from the exponentially distributed freezing times. We ran the simulation with the number of droplets big N taking on every integer value between 3 and 50, and with the parameter mu taking on thousands of values logarithmically spaced between 0.001 and 1,000. We also ran the simulation for 1,000 trials to get a distribution of possible omega values for a given N and mu. The resulting data set is a three-dimensional structure with big N on one axis, trial number on another, and mu on the last axis. These three cubes are a visual representation of our resulting data sets. We obtained a 3D output for each variable of interest, N-nuc, T-tote, and omega. If we select a fixed number of droplets, let's say big N equals 50, and focus on simulations within that plane of the 3D structure that produce a particular value of N nuke, say 5, the resulting list of omega values from these selected simulations can be considered a distribution of all possible omega values, which yielded 5 nucleation events from a starting population of 50 droplets. Here's a cumulative distribution function, or CDF, of the omega values from the same n equals 50 and n nuke equals 5 scenario that I described before. Now, if we assume that this distribution contains all possible values of omega for this given scenario, what we hope to see is some agreement between the equations from the COOP paper and the statistics of our simulation. This next plot is a CDF of the t-tote values from the same simulations as the omega distribution before it. We can see that the average value of t-tote for this scenario is around 515 seconds, which is the t-tote value we will use to calculate equations 10a and 10b from COOP that were shown before. Now, if we select some desired probability that the data is between omega low and omega high, we can use our values for n nuke and t-tote to solve for omega low and omega high from COOP. Here is the same CDF of omegas as before, but with a few things added. First off, the horizontal lines extending from the y-axis are meant to chop off the first 5% and the last 5% of the data from our simulation, leaving us with 90% of the possible omega values according to the computer simulations. The vertical lines are placed at the values of omega low and omega high that come from the COOP equations. If we use n nuke equals 5, t-tote equals 515, and choose a probability of 90%. Note that the lines intersect almost exactly on the curve for the CDF of omega values. These results suggest that our simulations are in agreement with the statistical claims made within the COOP paper, and thus we can use the COOP formulation or the statistics of our simulations to calculate an uncertainty bound on our J-het measurement. Here's the original plot again. Now here's the plot of J-het measurements with our new uncertainty bounds. We can now say with more certainty that the freezing behavior of water droplets on the mica treated with the aluminum trivalent ion is fundamentally different from that of the bivalent ions, which are also noticeably different from the natural potassium ion surface. These results suggest that the surface charge density plays a significant role in the heterogeneous ice nucleation, and thus the relationship should be further investigated.